Hello, students. Let's begin our journey into the fascinating world of metallurgy. Imagine you are following a treasure map, except here, the treasure is pure shiny metal and the path has several checkpoints. The extraction of metals follows a sequence, first preparing the ore, then concentrating or enriching it, converting it into oxide, reducing it to free metal, and finally refining it until it shines in its purest form. Along the way, we may even alloy it for strength or special properties. Think of it as baking a cake. You first prepare the ingredients, then process them step by step. Only at the end do you get the finished dish. Metallurgy is exactly like that. The type of ore and the reactivity of the metal decide which recipe we follow. Once an ore is mined, it is like a raw vegetable from the market covered in mud and stones. You can't cook it directly. Similarly, ores contain unwanted gangue like silica, clay, and iron oxides that must be removed. For heavy ores like tin oxide, gravity separation is used, the denser particles settle, lighter gangue is washed away. For sulfide ores, we turn to froth flotation. Collectors like xanthates make the sulfide particles water repellent, frothers like pine oil create bubbles, and the desired ore attaches to the froth, floating to the surface. Magnetic ores such as magnetite and hematite blends are separated using magnets. And sometimes chemistry does the job. For bauxite, sodium hydroxide dissolves the alumina, leaving behind the impurities. This is called the Baer process. For argentite, silver sulfide dissolves in cyanide solution in the presence of oxygen, a process called cyanidation. So, beneficiation is like cleaning and sorting the vegetables before cooking. It saves effort in later steps. Now that we have a concentrated ore, the next stage is conversion to oxide. Why? Because oxides are the easiest form to reduce. In calcination, we heat the ore strongly in the absence or limited supply of oxygen. A classic example is zinc carbonate. When heated, zinc carbonate decomposes to zinc oxide and carbon dioxide. The reaction is ZnCO on heating gives ZnO plus CO. In roasting, we deliberately use an excess of oxygen. Zinc sulfide, when roasted, reacts with oxygen to form zinc oxide and sulfur dioxide. The equation is 2ZnS plus 3O gives to ZnO plus 2SO. Lead sulfide undergoes a more complex roasting. 2PbS plus 3O gives to PbO plus 2SO, and the PbO can further react with SO to form lead and sulfur trioxide. These steps remove volatile matter and moisture, leaving behind an oxide that's ready for reduction. It's like preheating and softening ingredients before the actual cooking. Now comes the heart of metallurgy, reducing the oxide to metal. One way is using carbon or carbon monoxide. The general reaction is Mo plus carbon gives M plus Co, or Mo plus Co gives M plus Co. In the blast furnace, iron oxide reacts with carbon monoxide to form molten iron. The equation is Fe plus 3Co gives to Fe plus 3Co. The flux, calcium carbonate, decomposes to calcium oxide and carbon dioxide. Calcium oxide then combines with silica to form calcium silicate slag, which floats on molten iron. Sometimes hydrogen is used instead of carbon. For example, tungsten trioxide plus 3H gives tungsten plus 3HO. This is especially useful when carbon contamination is unacceptable. Another spectacular method is aluminothermy. Chromium oxide reacts with aluminium to form chromium and aluminium oxide, releasing intense heat. The reaction is CrO plus 12 gives to Cr plus AlO. This is the famous thermite reaction, strong enough to weld railway tracks. Each route is chosen carefully depending on thermodynamics and the desired metal purity. For some highly reactive metals, no chemical reducing agent works. These metals, like sodium, potassium, calcium, magnesium, and aluminium, are extracted only by electrolysis. Take aluminium as an example. Aluminium oxide, dissolved in molten cryolite sodium aluminium fluoride, is electrolyzed. The reaction is Alu gives to a liquid plus 3 by 2O gas. Cryolite reduces the melting point of alumina and improves conductivity. Similarly, sodium is extracted from molten sodium chloride in a Downs cell because in aqueous solution, water would get reduced instead. Remember the key relation, Gibbs free energy change equals minus NFE degree. If the electrode potential is very high, it means we need to supply a lot of electrical energy. In other words, electricity itself becomes the reducing agent. Once the crude metal is obtained, it usually contains impurities that reduce its usefulness. Refining is the polishing step. In electrolytic refining of copper, impure copper is the anode, pure copper is the cathode, and copper sulfate solution is the electrolyte. At the anode, Cu becomes Cu2 plus 2 electrons. At the cathode, Cu2 plus 2 electrons becomes Cu. Precious metals like silver, gold, and platinum settle as anode mud. For copper and tin, poling is done by stirring molten metal with greenwood poles. The gases released reduce metal oxides to pure metal. For semiconductors like silicon and germanium, zone refining is used. A moving molten zone pushes impurities to one end. For metals like zinc and mercury, distillation or liquation is used since they are volatile or have low melting points. So, refining is like the final polishing of a diamond, it brings out the true value of the metal. Let us now solve a real problem. Suppose we have 1 ton of chalcopyrite ore, copper iron sulfide, containing 2% copper. That means the ore has 20 kilograms of copper. The roasting reaction is to CuFeS2 plus 4O2 gives Cu2S plus 2 FeO plus 3SO2. In the converter, Cu2S plus O2 gives to Cu plus SO2. If metallurgical recovery is 95%, the blister copper we get is 19 kilograms. On refining, purity is 99.9%. That means the final cathode copper will be 19 multiplied by 0.999, which is 18.98 kilograms, correct to 3 significant figures. This shows why in metallurgy, we must always consider 3 factors: ore grade, recovery, and refining purity. Ignoring any one will give you the wrong yield. It's a common exam trap, so be alert.